Bom dia a todos. É um prazer recebê-los aqui. It's an honor to host Professor Elaine Weyuker and Tom Ostrand. It's very important for our institute to have you here. We know that you have more than international recognition for your activities, very relevant activities you have done for the scientific and technological development. So it's really nice to hear your experience and try to establish a future for collaboration, stronger collaboration from now on. Okay, and I will invite then Elaine to start the talk. Then after Elaine's talk, we are going to have Tom's talk. And in the afternoon, 2:30, we are going to have a short tutorial, 2 hours tutorial, okay? And Professor, both of them, in fact, Elaine and Tom, they work in the direction I like very much, very close relation between academy and industry, right? They have very excellent experience in academia and industry. So this is the most important part, let's say, I'm looking at nowadays, because I understand that the future is to have a joint cooperation with the industry. Okay? And, so let's hear Elaine. I'm really happy to have you here. Okay, thank you.
Do I get a free pair of glasses too?
You can.
Okay. Well, I'm very excited to be here. Jose invited me 25 years ago, and it took a long time to get here, so I'm very excited. I'm going to talk about this morning some work that Tom Ostrand and I have done for the last 10 years or so. And as Professor Maldonado said, I was an academic for many years, and I moved to an industrial research lab because I felt that, number one, I needed data. I needed access to real systems. And as an academic, even though I was quite successful at what I did in terms of publishing and things, it had no real impact because it wasn't done in connection with industry, and I couldn't show that it was real. And so I moved to an industrial research lab where, where I could do that. And so this was all done at AT&T Labs. And this morning I'm going to talk about Tom and I will both talk about the technology. And then in the afternoon we'll give you a picture of how and why collaborations like this are so important. Okay, so, oops, is this not on? Is it on? All right, the goal of this research is to identify the files of a very large, long-lasting software system that will have the largest numbers of bugs in the next release of the software. So why is this important? Well, initially, our thought was, if I could say to a tester, before it goes to system test, this file, this file, this file are the ones that are going to have the largest numbers of bugs in the next release, and I could do that accurately, what would it mean for them? Well, what would you do? You would test there first. You would test there hardest. You might assign your best people to work there. You'd allocate enough time so that you could thoroughly test that part of the software. And when we started speaking with development organizations about this, because we felt that we had to collaborate with them throughout the whole project, they said, well, you know, developers are also very interested in this, because if I could say to them, look at this file, it was a problem back here, it was a problem back here, and I know that in the future it's going to be a problem, they might be able or might be willing to put special resources there, things that they don't normally do because they're too expensive, do code reviews, do design reviews, do architecture reviews, which are very, very expensive and very labor intensive, or even just completely re-implement this part of the system, because they know that this is going to cause problems, and they want to make sure that it doesn't cause problems in the field to their customers. And finally, if I'm a project manager and I knew that these parts of the system were the most problematic, I'm in charge of allocating who works on them, so I put my best people there. I'm in charge of allocating time schedules, so I give enough time for that. Etc. So there are a lot of stakeholders, there are a lot of different people who are interested if we could do this. Okay, so the first thing that we did was to verify that bugs were non-uniformly distributed among the files. Now, why did we do this? Everybody knows, and as soon as you hear everybody knows, you know that that's just folklore. Everybody knows there's a Pareto-like distribution. 20% of the files account for 80% of the bugs. But when you look in the literature and look for scientific studies or empirical studies that have shown that, you don't find them by and large. And so the first thing we did was to get a real system that had been in the field for 3 years, that had 12 releases, and see, do we see in this system a very non-uniform distribution? Why is that important? Well, if all files are the same, then what does it even mean to say I'm going to find the worst ones? They're all the same. So you want to make sure that there are some that have a lot of bugs, and then most of the rest of them have few or no bugs. So we did that. We verified that there was this Pareto-like distribution. And then once we did that, we looked at these 12 releases, and in each release we said, let's look at the worst files, the ones with the largest numbers of bugs, and see what they have in common. See what kind of characteristics all the bad files have. Okay? And what we were doing is looking for characteristics that correlate, are usually associated with bad files. That doesn't mean they cause them, that we can prove, but what we can say is that they seem to go together. And if we could find the files that have these characteristics that seem to correlate with fault proneness, that would be very good. So what we found was eventually that if you had 5 very simple pieces of information about each of the files, you could make very accurate predictions. And the 5 things were, in roughly the order of importance, the size of the file. And if you think about it, for the last 25 years, the most important underlying characteristic of software engineering has been to tell people big is bad. You have to modularize a system. And we found that. We found that the big files, the ones that they put too many things into, were the ones that caused a lot of problems. We found that if you've changed the files recently, The more you've changed the files recently, the more likely they are that you've introduced bugs. We found that if it had a lot of bugs recently, it's going to continue to have bugs. Once buggy, always buggy. We found that if a file had been in the system for a long time and had not had a lot of recent changes and had not had a lot of recent bugs, it was very unlikely to have bugs. Whereas if it was new to the system, it was very likely to have bugs. And finally, some languages have much higher fault rates than others. This was the least important characteristic, but it was statistically meaningful. So we took these 5 characteristics of files, and we weighted them based on what we found the importance was, and we built, eventually, a statistical model. The statistical model that we used was negative binomial regression. And I'll say a drop more about that later on. But basically, the reason that we chose that was one of the nice things about working in an industrial research lab was the man whose office was next door to mine was a statistician, not a computer scientist. And although Tom and I started our lives as mathematicians and both studied statistics, and we could understand it and we could do it, we had no intuition. And statisticians have intuition. He had no intuition about software systems that we did, but he had lots of intuition about statistics and modeling and data. So I went to him and I said, what kind of a prediction model would you recommend? And he said, negative binomial regression. He looks at my data like that. And I said, well, how did you decide that? He said, your data screams it. And as I say to people, it didn't even whisper it to me. I mean, so, okay, so all of the systems that we studied, and we studied 9 of them, and we made predictions for 170 different industrial releases of systems, they all use the same configuration management system. They were all systems that used the one that AT&T used. And in this system, it was both a version control system and a change management system, or a bug reporting system. And so we get all of these 5 things I mentioned before, we get from the database, because anytime you want to change the system, you need to initiate a modification request, or an MR. Okay? And it says, I want to change the system, and here's why I want to change the system. So a system tester will say, I ran this test case, and this is what happened. But that's what should have happened. And then they send it back to the system tester. Or you might be a developer and you're adding new functionality, which is a change but not a bug. And so you say, I'm changing the system to add this new feature. Okay, so there's all kinds of information that's in a repository or a database that underlies a system. And we mine that database to extract the data we need to make the predictions. Initially, we did this manually. So to start with, we didn't know whether or not this was going to work. So we started with the first real system, and Tom and I read every single modification request, and this was a 500,000 lines system that had been in the field for three years. Every system that we deal with runs continuously. It's a 24/7 system, and they're constantly in the field. They're constantly used. We read every one of the modification requests. We decided which ones were bugs and which ones were not. We had expected that in this change, in this modification request system, it would say, is this a bug? Yes, no, I don't know. But they don't. They don't do that. So we had to decide, how will we know when things are bugs or not? How will we know when it's a change? And we initially tried reading the English language comments that they wrote, and some of them were clear. I ran this test case, I saw this, it's the wrong answer, it should have been that. Most of them, when you went back to them and said, what did you mean when you wrote this? They'd look at it and say, I don't know. So even they were. So we had to find out a way of automatically determining what were bugs and what were not bugs, which was a problem we hadn't anticipated having to deal with, but I'll mention that in a little while. And then we had to decide, were they bugs and what kinds of changes were made to files. See, I see a difference. Okay, and eventually, for the first two systems, we did everything manually because we wanted to make sure that we really could do these predictions. And then for the third system, since we got such good results, we then built a tool, because if you don't automate, no one will use it. And if you don't automate and make it easy, they will not use it. And if they have to know statistics, forget about it. And if they have to understand your research, forget about it. So it has to be magic. Your tool has to be magic, or nobody wants to use it. Anyway, that's just a hint of what's coming this afternoon, how to make magic. And so eventually we built a tool where the data mining was automatic. It converted it to an intermediate form, basically a tabular form, a table, and then it sent it to our prediction engine, which was automatic. Okay, and out came test me first, test me next, test me after that. A sorted list of files that were predicted to have the largest numbers of bugs. Okay, so as I said, the predictions were made using a negative binomial regression model. A lot of the literature, a lot of the fault prediction literature, which is by and large doing something a little different than what we did, uses machine learning algorithms. Those are very popular in the research literature, not popular in industry. But we tried them. We looked at recursive partitioning, we looked at random forests, and we looked at a Bayesian technique. And what we found was that none of them outperformed negative binomial regression. Negative binomial regression was significantly better at making predictions than recursive partitioning in the Bayesian system we used. Random forest was roughly the same, but at least for the systems that we tested, was far less efficient, was much slower, okay? And so we stuck with negative binomial regression, and the bottom line was nothing that we looked at outperformed that. Okay, our tool ultimately consists of two distinct parts. The first part is the back end, which is the data extraction. And our vision was that we were going to have many different backends. So we use this system that was common in AT&T, but maybe you use ClearCase, or maybe use Git, or maybe use some other open source repository. And so we'd have a different backend to extract the data that you need, and then you transform everything into an intermediate form, so it didn't matter where you got the information from. The backend would translate it into a standard tabular form, and then there'd be a single prediction engine at the front. Well, it turned out that that there was a never-ending supply of AT&T projects that wanted to try this, and they all use the same database system, the same modification request system, and so we had only one back end. We were just speaking to an AT&T subsidiary that used Git instead, and was very eager to try to have us do a back end, or for them to do a back end for us. When the plug got pulled. Anyway, I'll say more about that in the afternoon. So we have only one back end. So we have one tool which I'll show you a little bit about. As I said, it makes a prediction of the number of bugs that will be in every single file in the system in the next release. So it predicts an actual number, and then it sorts those files in decreasing order of the predicted number of bugs. Okay? We never tell people how many bugs it was predicted to have, because one of the things we discovered is if you tell people this file will have 10 bugs, the minute they find 10 bugs, that's the end of the game. They say, well, I found them all, goodbye. And so the actual number of bugs that are predicted are not that accurate, but the ordering is very accurate. And that's the important thing. So that's all we tell them. This is worst. This is predicted to be worse. This is predicted to be next worst. This is predicted. And you'll see on the system. And then it displays the results to the user. Okay, how do we decide now? So there are two parts of us. We're interested in producing something that practitioners can actually use to make their software better. But we're also primarily researchers. And so we're also interested in doing science and publishing papers. And so you need, and what's very nice for us is everything we do comes with these large empirical studies to validate them. And that's very, very important. And so how are you going to measure success? And that's something that you need to think about whenever you do empirical studies. How will I know how well I'm doing? What is success going to mean? So what we said, the way we define success is we predicted the number of bugs that will be in each file in the next release of a large software system. We sort the files in descending order of the predicted number of bugs. And typically we say, let's see, the way we're going to validate this is let's see what percentage of bugs actually turned out to be in the files that we defined to be worst. And you could pick any value of n. Typically, since everybody knows about a Pareto distribution, 20% of the files should account for 80% of the bugs roughly. That's what we used to decide success. What percentage of the actual bugs in the system turned out to be in the worst 20%, the 20% of the files we predicted would be worse. And we looked at some other measures that scientifically were very interesting, and we talked about that in some of our papers. But in fact, practitioners didn't understand what we were talking about, and so we stuck with something that they could understand. So we could go to them and say, look at system X. In release 3, we predicted that these files would account for the vast majority of the bugs. And in fact, they accounted for 82% of the bugs. And in release 4, these files were predicted to account for the majority of the bugs, and they accounted for 85% of the bugs, etc. And that they could understand. That, that was the thing that won them over to wanting to use the system. Okay, so here are 9 systems that we looked at, and let me tell you, and these are all real industrial systems, and let me tell you something about them. The first one was an inventory control system. It was a little more than 500,000 lines of code. Let me see. Yeah, so this one was a little more than 500,000 lines of code. We followed it for 4 years and 17 releases. Most systems at AT&T and many large companies have quarterly releases, quarterly major releases. And that means that new functionality, new features are added once a quarter. Okay, and what we found that averaged over these 17 releases, the files that we predicted would be the worst 20% contained 83% of the real bugs that happened over this 4-year period. Well, that's an enormous win. If I can tell you with good accuracy, look here, look here, look here, what are you going to do? And you've seen that this really works. What are you going to do? You're going to put your best people there. You're going to say, okay, I've got to test everything, but I want to test these hardest, I want to test these first, etc. Okay, so we were very excited about this first system, but the first system was the one that we used to determine the characteristics to build the statistical model. So then we started to worry, maybe the reason it worked so well for this system was this was the system it was designed for, and would it work for a different system? So NP was a Java system. 75% of the files were written in Java, and then there were small percentages of files in Perl and C and all kinds of awk, all kinds of different language, SQL. And so the next system, when we showed, one of the things that was important was making sure that practitioners knew about it. So we used to have a once-a-year software symposium, which was meant for practitioners. Most of the talks were given by researchers. Most of the researchers who gave talks on things that the practitioners thought were irrelevant. This they thought was very relevant, and so I gave the keynote address there. And I talked about this system and what we found, and I said, so anybody in the audience, and here's hundreds of testers and software developers in the audience, I said, anybody who likes what you've just heard here, here's my email, here's my phone number, call me, and we'll come right over and work on your system for you. So I wasn't back to my office before I get a call from the woman who headed testing for this project, who said, do me next, try us next. And so this was a very different system. This is what's called a service provisioning system. Basically, it's a database system which initializes your customer service. So if you're a telephone company, you call up and you say, I need a new telephone, and they have to start your service. So it's a database system. And we started them when they were just getting into when they were just in development and were just getting into system test. We followed them for 9 releases for 2 years. This was a little under 500,000 lines of code. And this was written in, so this was a Java system. Because this was a database system, the largest numbers of files were written in SQL. That was about a quarter of the system, and this was a much more heterogeneous system, so they had files in C and files in everything else. And we thought this was a very heterogeneous system, because the largest number of files in one language was about a quarter. And we still made exactly the same results. The top 20% that we predicted would be the worst accounted for 83% of the real bugs that they found over time. Okay. The next system that we looked at was very, very interesting. In this case, they weren't so eager for us. In this case, their management was eager for us because this was a project that was considered in chaos. They had what they called continuous releases. Now they would call themselves an agile project. But what it was they were testing, changing, throwing it out. Every night they had a new build. Every night new code went out, and it was thrashing. And so their management had heard about this and said, maybe you can help them. And so this was a challenge for us because our project was predicting the future. And what do we mean by the future? We mean the next release, based on what happened in the past. And what do we mean by the past? We mean earlier releases. Well, here, instead of having these nice quarterly releases, which have a fixed process. So typically, if you have a 3-month release, halfway through it's 6 weeks, all code is frozen, no changes are made, it's sent off to an independent system test organization that has nothing but professional testers who do nothing but test it, and when they find a problem, they send it back to the developers and say, fix it. Okay, so the only changes that are made are to fix bugs. At the time the code is frozen and sent to system test, the next release of the software starts. And so you always have a minimum of 3 active releases. 1 is in the field, 1 is in system test, and 1 is being changed by the development organization. Well, here we had hundreds, thousands. Who knew? Who was using what? This was an automated voice response system. Okay, and I don't know if you know what those are. Those are the kinds of things you call and you want to speak to somebody because you have a problem, and you never get to speak to anybody. They ask you questions that they don't understand, that your program doesn't understand, and tries to solve your problems because speaking to human beings costs money. And speaking to this program doesn't cost money. So you want to solve everything with this voice automated system. Anyway, so we had to figure out how are we going to make predictions when the development process doesn't match what we expected the development project to be. Also, we thought that WN had been had been a heterogeneous system. In fact, VT had 34 executable different languages, had files written in, we didn't even know that 34 executable languages existed. Often we couldn't tell what they were. I mean, and this doesn't include WAV files, which are non-executable. It doesn't include doc files. It doesn't. These are so they would make up a language, write one file in it, and you'd have to try to guess what it was. Anyway, so what we decided the solution was we would just make synthetic releases. We would just look at the calendar and say January 1st, April 1st, July 1st, October 1st are new releases. But there's no big system test period, so we didn't know whether the predictions would work. And in fact, they worked not badly. I mean, we still were getting the vast majority of the bugs. So there's something about these characteristics that have nothing to do with the language the system is written in. Doesn't seem to matter whether it's more mature or less mature. Doesn't seem to matter what the development process is. We can still. So that's when we built the tool. The next three systems were very, very interesting because they were written by a different company. They're written and maintained by a different company that use the same change management version control system that AT&T used. The way I got them is the president of the labs was a big fan of mine. So I went to my boss, who was not a president, and I said, I'd love to try some other companies to see to what extent this works because AT&T has this certain kind of culture. And I said, do you have any idea where I can get other software from? And he said, no, I mean, who's going to give you software? He said, but why don't you call the president and maybe he'll know. So I said, well, why don't you call the president? He said, because when I call him, he'll say no. When you call him, he'll say yes. So I called up the president. And he said, oh, that's really a great idea. He said, let me think about it and wait about a week, and I'll try to have some other systems for you. So one of the things you find out, the presidents of big companies, friends are presidents of other big companies. And when Elaine Weyuker calls, they say, what, are you crazy? And when the president of another company calls and they play golf with them, so the next thing we know, we got a call and we got these three systems that use the same repository we did. And these were very mature systems. These two were in the field almost 10 years each, and this one was in the field for 7 years. So we had lots of releases to make predictions for. They were of comparable size. And our results were very interesting. We got, these were basically C projects that had been converted to C++ projects, which basically meant they were C code and they ran with a C++ compiler in most cases. This was a C++ project. Okay, and what we got was roughly the same results. And then these three were larger. This one was more than 1.5 million lines of code. This was over 2 million lines of code, and this was the smallest project that we got at under 300,000 lines of code. And what's interesting is the biggest ones did the best, actually. So size didn't matter, functionality didn't matter, language written in didn't matter, company didn't seem to matter. age, maturity didn't matter. We got very similar results for all of them, which was very, very exciting. Okay, and now this just shows the last columns, the last column in the tabular form. This says that this is the percentage of actual faults that occurred in the worst file, in the files that we predicted would be worst. So if you look at the first system, we got 83% of the real bugs that happened in the real system with real customers, okay? So now we started thinking about, well, what about the other 17% that we didn't find? And there were two possibilities. One was that there were one or two terrible files, and we're missing them. And I would say if that happened, this isn't working very well, because you should never miss a terrible file. The other possibility is you've got a lot of files that have one or two bugs in them, and that's what we expected. But we had to see what the situation was. And so that's what this shows. And we did this for every system, and you see exactly the same thing. So let me explain to you what this means. So this is release 3 through release 17. We usually start making releases, predictions for starting at release 3, because our model looks at the number of changes you had 2 releases ago. You could start release 2, then you have less information. Okay, along the x-axis is every file in the system, and they're ordered based on the predicted number of faults. So the file that was predicted to have the largest number of bugs is right up at the y-axis. And the ones out here are predicted to have no bugs. The y-axis says how many bugs were actually in that file. So if this was working, and the red dotted line is the 20% mark. So if this is working perfectly, if this is working absolutely perfectly, you'd see a monotonically decreasing graph, essentially. What you see is almost that. What you see is all the tall bars are to the left of the 20% mark, and these out here are files that have either no bugs, if there's no bar at all, or 1 bug or 2 bugs. What you'd like to see is something like this, where the tallest bar is right up next to the axis. That means the file that you predicted would be worse really is worse, and the file that you predicted would be next to worse is next to worse, etc. And so you've got almost perfect prediction here. In no case do we have any tall files that we missed. So this is very good, and we saw this for all the systems that we looked at. Okay, and now I'm going to tell you a little bit about the tool and what you need to know. And this is what wins it for customers, for potential customers or users. Okay, so you've got a person, and know that she wears purple. That's very important. Everything that I have to do with is purple. So she gives some parameters. She inputs some parameters to the tool, and she says what release she wants to make a prediction for. And then it goes out, the tool goes out to the version control change management system, and data is extracted from that, and her information and the stuff from the database goes into the statistical analyzer and sent to the prediction engine. She says what she wants to make a prediction for, and out comes the input. And here's an example of a very simple interface, GUI interface that we built. Okay, so, to start with, the user says, what's the name of the system? And this is a real system we just changed the name of. All right, so think about what you need to know. You're the user. You need to know the name of your system, not demanding a lot. And then the tool automatically puts in every release that's in the database in chronological order. So it goes out to the database and it says, okay, you've got the following releases. You've got, this one named it by quarters. You've got 2007.2, you've got 2007.3, you have earlier releases. This is a scroll bar, etc. Okay, so it told you this. You didn't even have to know that. Then it says, what do you want to call a bug? And as I mentioned to you earlier, the system doesn't say whether something is a bug. When you initiate a modification request, you don't say, yes, this is a bug. We tried to get them to change it. It wasn't wholly successful. The people who own the underlying modification request system thought it was a great idea, but the projects didn't think it was a great idea. So a few projects did that, but most of them didn't. But they were willing to say, what is a bug? So most of them, we went to them and we talked to them and we said, well, how would you know whether it's a bug or not? And they said, if system test finds it, it's a bug, because that's all system tests, that's their sole job, to find bugs. They don't get to say, hey, I wish this system did this. They just run test cases and look for things that are not right. So usually, if it was found during system test and we change something, which we can tell from the configuration management system, then it's a bug. Some other projects said, in addition to system tests, if it's found during a later stage, what we call operations readiness or end-to-end testing, they would also count it as a bug. If it's found in the field, they would also count it as a bug. And so what the user can do is select as many of these stages as it wants. This is populated, the phases is populated by the tool. Anytime that something is changed and during a particular stage, it puts it into the database. So this user said anything that was found in system tests is a bug. He could have said anything that's found in design is also a bug. That's up to the user. Okay, the next thing the user is asked for is, what kind of files are you interested in looking at? What are files that you're worried about testing? Okay, this one said, I'm interested in C files, I'm interested in C++, I'm interested in Java, and this is a C++ with an embedded SQL. So this is a proprietary language. He could have picked other languages. All right, this user picked 4 language types. And then it's asked, what release do you want to make a prediction for? And usually it's the most recent release. This, I think, is a typo, actually, because this, I think, was actually a typo. Okay, and then they're shown, you asked for to make, you asked to make a prediction for 2008.2. The name of your system is Bluestone. You said you want to count system tests, things found during system tests as bugs, and you're interested in these 4 types of files. And so, is this what you really wanted? And he says, yes. And then it says, where do you want to put the results? And he picked the config file name for that release. And then you pull the handle and it runs. So what did you need to know? What does the user need to know? The name of his system, what release he wants to make predictions for, what kind of files he's interested in. He could have said, I'm interested in every kind of file. What he wants to call a bug, and where he wants to put his results. Did he need to know anything about data mining? No. Did he need to know anything about statistics? No. Did he need to know anything about what were the characteristics we're using to make the predictions? No. In other words, as far as the user is concerned, we're providing magic for them. Okay? He puts in his system, and out comes a list. And what he has is choices. He says, all right, how do you want us to show you the thing? And the default is, show us in decreasing order of predicted numbers of bugs, okay? Which languages do you want us to show you? Well, this one says all of them, and this says 100%. But he could have picked any percent, or he could have isolated it to any of the languages. And this was a kind of unusual system, because one file, we just changed the names of the files, but this is the 21 files predicted to be worst, and they were predicted to account for 77% of the bugs. They were all Java files. One file was predicted to have more than a third of the bugs. And then it went down quite rapidly from there. This is unusually skewed, but real. He could have said, I'm only interested in the file, oops, sorry. I'm only interested in the EC files, in the C++ with embedded SQL. Oh, well, they accounted for less than the top 21 files accounted, and this is a scroll bar, you could just scroll down, accounted for less than 1% of the bugs. So he could have said, I'm only interested in the worst 10% of the files. Normally we look at 20%. Another way that you can look at it is to look at the files that collectively are predicted to account for 90% of the bugs or 80% of the bugs. That's another way that you can use it. So this, if you only want to look at the files that accounted for 77% of the bugs, they all fit on this without scrolling. Okay, to give you a sense of what it took, so the hard part was coming up with the algorithms, was deciding what were the characteristics, building the statistical model. Once that was done, building the tool itself was not a big deal. So the data extraction was basically done in Python, and consisted of 750 lines of code, not a lot of code. The prediction engine, so initially when we started doing it, we were using SAS, which is a commercial statistical package, which has a very expensive license. And we knew that no project was going to be willing to plunk down the money for that license. But we wanted to be able to do it quickly, and our statistician had a license. Once we had that, once we knew that we could make the predictions, Tom wrote R scripts. R is an open source statistical package. It originally came from S, which was a labs built system, and then they spun off a commercial tool, which was S++, and then they started this open source R. So, Tom wrote the statistical engine in R, using R scripts, and but AT&T had a rule that you couldn't use open source systems in anything that touched the network, even though it was written by us and not us, originally by the labs, and maintained. Most of the prominent people are from the labs. It still was open source. The answer was no, and so we got a development professional programmer who was interested in being part of our patent application, and he wrote, on a weekend, he wrote a new statistical package. It was 2,100 lines of code, compiled to 75K, and basically he wrote it literally over the weekend. And so that's just to give you a picture of once you have the algorithms, once you have the idea, once you've validated that things work, the tool itself, and of course we have a primitive prototype GUI, but the tool itself was not the big issue. We only ever did one back end, namely the configuration management system that AT&T used internally. I mentioned that this other company also used the same configuration management system. We had a proprietary version of a commercially available configuration management system, which is a long story. Anyway, other factors that we looked at were the number of developers, both in terms of counts and individuals. Okay, so when I started giving these talks, the first question that I could always count on somebody asking was, why didn't you include developers in your prediction model? Okay, I know that Sam is great, and I know that John is terrible. If John wrote the code, it's got a lot of bugs. If Sam wrote the code, it's got no bugs. And everybody thinks that that would be the most important characteristic. And Tom, initially, we didn't look at that because we were dependent on development organizations to give us code to look at, and if they were afraid that they were going to get evaluated based on what this tool said about them, we weren't going to get cooperation from them. But in fact, Tom is going to talk about, after the break, is going to talk about what we learned when we looked at both Sam and John, and also the number of different people. So you also have the sense of too many cooks spoil the broth. I don't know if that's an expression in Portuguese, but if too many people touch it, they're going to really mess it up. You're going to put in salt, and then you're going to put in pepper, and then you're going to put in this, and you're going to put in this, and nobody bothers to see what everybody else has put in. And so we looked at the number of developers and other characteristics that Tom will talk about, and he'll tell you about what we learned. We also looked at calling structure. So the idea was, well, if this is buggy and it passes stuff to these files, are they likely to be more buggy? And similarly, if they're getting things from buggy files, or if they're buggy and are getting things from files, are the ones that are passing it, are they buggy because they're getting past bad stuff? And the third thing, another thing that we looked at was we only counted the number of changes in our prediction models. What happens if I look at how many bytes are changed? Did I change, I found one character had a typo, or I added 40 lines of code or 100 lines of code or 1,000 lines of code? Does that make a difference? And Tom's going to talk about these things after the break. So that's it. After the break, Tom's going to tell you more about it. In the afternoon, in the short course, I'm going to tell you more. Mostly, I'm talking about other projects, but I'm also going to say a little bit more about this and some of the secrets of the universe. Okay, any questions?
I have one comment. Well, for sure, Elaine has described it as a very rich scenario in terms of an experience in industry.
Right.
Because learning how to deal with managers, developers, and the owners of the company.
And that I'm going to talk about in the afternoon.
Yes, so it's a very rich scenario to make this kind of tool available and successful in industry. It's not an easy task, even though you are inside them.
Yeah.
So it would be nice if you look from different perspectives and take this opportunity to address some specific points. And I have one, but somehow I missed in your prediction model the quality of the testing activity. Does it matter or not? Another point is that if we, since you are very expert in testing and all this, I was curious about, I didn't see any information on the test activity behind those systems. And another point is, if I have an industry here interested in your tools and your concepts and so on, how could we collaborate in terms of open source or try to have a system that would be open and try to help the industry to collaborate and provide a large amount of data would be really great in this sense.
Okay, those are two really, really good questions. The first one, the prediction model did not include any kind of assessment of testing. On the other hand, as I mentioned, with the exception of the system that the automated voice response system, AT&T had a very rigorous process. So you have a quarterly release, say a 12-week or 13-week release. Halfway through, the code is frozen. The remaining half of the time, the remaining 6 weeks, is nothing but testing. Before the code is frozen and goes to testing, the development organization does their own unit testing and integration testing. Initially, every single project is required to go through, before the first release, an architecture review, a design review, a code review, at the very minimum. Those are very expensive, very intensive. Normally, it's only before the first release, but it does not go, they cannot start writing a line of code until, because they found that if you start writing code too early, before you've carefully designed the architecture, before you've carefully done a low-level design, it's too late to go and find out, oh, I need to know this, or I need to have an expert in that, once you've started writing code. And so all of these projects have a very, very rigorous and independent quality assurance process going on. And they were mostly the people that we interfaced with. The other thing is, in many places, testing is where you send your failed programmers, the ones who are no good you make them testers, or the ones that are just beginners. At AT&T, that's not the case. At AT&T, historically, testing was considered very, very important. It was very common for people to rotate in and out of, so you'd be a developer for 3 years, and then you'd be a tester for 2 years, and then you go back, because the people who are best at finding bugs are people who know what kind of bugs people make because they've made them. And the people who are good at not making bugs are the ones who understand what kind of bugs people make. And so you get better developers by having them be testers, and you get better testers by having them be developers. And the goal is, there's a group at Microsoft Research that's done some very interesting fault prediction work. They only look at, and they're very good scientists, let me say it, Zimmerman, and he worked with Zeller as a student, who's an academic, but Zimmerman and Chris Bird, very good scientists, but they only look at post-release bugs. If at AT&T we only looked at post-release bugs, there are almost none. Microsoft is a kind of different situation in terms of post-release bugs. And they say, well, why are you looking for... So our goal is to find all the bugs before it goes to system test. You run this tool before it goes to system test, so the system testers can take advantage of it, can say, how should I tailor my testing? And their attitude is, it's not a bug unless your customer finds it. Our attitude was, at AT&T, we never want our customer to find the bug. So it's a different mindset. And so testing is very, very rigorous. Okay. The only project that did not have the same kind of rigorous was the one I mentioned, the automated voice response system. And that was truly considered an anomaly, that project. And that's why management sent us to them. In terms of open source, I think, now as I said, we've only worked with one backend, but we spoke with some companies in Sweden. I think that we could speak with companies who could, and we could not, all you'd need to do is build a back end, and then that puts the data into this intermediate form. And since we already know what the data is, and then pass it to, we know how to do the prediction model. And as a matter of fact, Alberto, who works for Siemens, and he's particularly interested, and I'll say something more this afternoon, he's interested in performance testing. He doesn't do correctness testing, he does performance testing, and I'll talk about that this afternoon. But Tom and Alberto and I are collaborating on doing some research that he's using for Siemens, use our prediction stuff. So we've been looking at his data in the back end, his repository, which is a little different than ours, and then we're writing a new R front end. So I think if a company was willing to commit some resources, it would not be so hard for us to help them build an open source system, especially using something like R, and using, if they use an open source system like Git. And that's why we were very disappointed that when this AT&T subsidiary that used Git wanted to try to do that, that AT&T decided that we didn't want to do that. But, so I don't think it would be a big deal. I think if they spent some time speaking with us, they could build an open source system, or they could build one that's tailored for their, however they collect data about bugs.
I have a further question.
It's a little hard to hear you, actually, because there's a blower going.
I have three little questions. Okay. One is, how willing is AT&T to apply this to other projects?
I will tell you more about that in the afternoon.
And the other one is regarding the quality management. If you give any sort of information for the project managers or any guy who handles quality.
Yes, and so in my first or second slide said, we thought of this initially as being useful for the quality assurance group, for the testers. But in addition, it's very useful. They said to us, it's very useful as a project manager, because the project manager is the person who allocates people and who allocates time and who allocates money. And so if they know before the release, before it goes to system test, that these are the worst ones, they're going to use it to assign, he's a really good tester and he's a really good tester. These are my two best testers. I'm going to assign them to these worst files. And I'm going to schedule the most time for the worst files, and for the ones that are predicted to have no bugs, I'll test it, but I don't need to. I can put my beginners on that. I can put the least amount of time on that. And in terms of using tools, which are sometimes very expensive to use, I'm going to allocate that for. So they found that, or they believe that for project management, this was also a wonderful tool for them. Wonderful information. Yeah.
The last one, just out of curiosity, does any project had automated tests before delivering to the test team?
By and large, surprisingly, no. You read the software testing literature, and we've come up with these wonderful ideas. And when you talk to the people who do it, and that's one of the things I'm going to talk about too, there's a disconnect between research and practice in general. So we couldn't even find projects that use code coverage, and these are AT&T is very, very careful about quality and takes it very seriously. I mean, when I moved there, I had been consulting for different companies, and I moved to AT&T, and I was really surprised that how seriously they took. So it was not uncommon for a project to have 700 developers and 700 testers, and equal size testing and development organizations. That's a lot of money. That's taking it back. But on the other hand, they viewed telephony as life critical. So you have to be able to pick up the phone every single time. You have to get a dial tone every single time. Your call has to connect to the right place every single time. And if you don't, you have catastrophes. So it was viewed very different than you know, you're a cable company, well, you know, it's entertainment if it doesn't work. I mean, we were shocked when we first got cable television. Half the time it didn't, and we had a cable modem. Yeah, you call up, it doesn't work. They say, oh, well, yeah, it'll be back tomorrow. You know, it had a so they took it very, very seriously.
Another one?
And incidentally, they paid testers well. I mean, that was another thing. It wasn't second-class citizens. Testers were paid like developers very well.
And then the last point, it seems to me that your tool to be useful as a kind of software development process precondition, in the sense that you have to have at least a good process, a good soft quality assurance system in the organization. So what is the kind of company I can address with this?
Okay, but we have the one, so we don't know. And the company that we spoke to in Sweden does train control systems. Obviously, life critical, really worried, really takes it all very seriously. Okay, but on the other hand, we did work with this one project that did not have good process. And although, if you recall, the 20% of the files that we predicted would be worse contained only 75% of the bugs. But still, that's the majority of the bugs. It's still catching the problems. And they did not have good process, and that's why we were asked. The others said, yeah, we'd like you to do this, because they had good process and wanted more good process. And they wanted a tool that could work on there. And the way to win them over is to show them, here's a project, a real project, and you probably have friends who work on this project. That sounds a lot like yours. It's roughly the same size. It's 24/7, and look at what we got for them. Would you like us to get the same things for you? And the answer is yes. For that system, and so they were very eager. For that system, they were not so eager to have us. And their management wanted us, but we were able to do good things for them. So I don't know.
Thank you.
Okay.
Then come back, please. Okay?